Far below the surface, darkness comes early. Not because there is no light, but because light dies fast in the ocean. Colors disappear one by one until everything collapses into a dull blue haze. Edges soften, shapes dissolve, distance becomes hard to judge. And yet, in that fading world, whales communicate across entire ocean basins, and submarines stalk each other without ever seeing a single clear silhouette. They don't trust sight. They trust something else. They trust sound. This first episode explores why sound, not light, is the main carrier of information underwater, and why any serious submarine is, in practice, built far more like an ear than an eye. When you step into the sea near a beach, the underwater world still feels familiar. You open your eyes, see the sandy ground, maybe some stones, maybe fish a few meters away. It feels like a dimmed version of the surface. But if you dive deeper, or if you swim into murkier water, that familiar picture collapses. 10 meters of visibility, 5, sometimes just the length of your arm. A flashlight helps for a while, but only close up. Beyond that cone of light, there is just darkness and guesswork. Light is made of electromagnetic waves. Water is very good at absorbing and scattering those waves. Reds vanish first, then oranges, then yellows. Eventually, even blue fades into a grey-green blur. Light loses its energy to heat and to a soft, directionless glow suspended in the water. Sound behaves differently. Certain sound frequencies can travel tens or even hundreds of kilometers through the ocean with surprisingly little loss, especially if you pick the right frequency and the right depth. That single fact, light dies quickly, sound can travel far, is the reason hearing beats seeing underwater. Before we even say the word sonar, one idea matters most: the speed of sound. In air, sound travels at roughly 343 meters per second, about 1 kilometer in 3 seconds, fast enough that thunder arrives only moments after lightning. In seawater, sound travels at around 1,500 meters per second, more than 4 times as fast as in air. Water molecules are packed much more tightly than air molecules. They pass tiny pressure changes, the compressions and rarefactions that make up a sound wave, very efficiently from one to the next. One sentence example: if you could clap underwater and stay safe doing it, someone at the same distance would hear that clap much sooner than in air, simply because sound races faster through water. For a submarine, this is not just a physics curiosity. It means that the ocean is full of rapidly moving information. Pressure waves constantly spreading out from ships, storms, animals, ice, even distant explosions. The ocean becomes a 3-dimensional field of sound. Whoever can read that field has an advantage. But speed alone isn't enough. Sound also dies as it travels, through absorption. Absorption means that part of a sound's energy is converted into something else, usually heat, as it moves. The farther a sound goes, the more energy it loses, and that loss depends strongly on frequency. High-frequency sounds, sharp, bright, hissy tones, carry a lot of detail. You can encode complex patterns, fast changes, crisp edges, but those sounds get absorbed quickly. Low-frequency sounds, deep hums and rumbles, carry less fine detail, but they can survive over much larger distances, slipping through the water like a slow, heavy pulse. One sentence example: a distant ship's low engine rumble can still be detectable long after a nearby, high-pitched clang has vanished into the background noise. This is why whales, long-range sonar systems, and global undersea listening networks often rely on deep, slowly changing sounds when range matters more than razor-sharp detail. Blue whales use extremely low frequencies, sometimes below what humans can hear at all. Their calls can cross entire ocean basins, bent and guided by layers of temperature and pressure in the sea. In the mid-20th century, scientists discovered a natural long-distance channel, the SOFAR channel, a depth band where sound can get trapped and guided over enormous distances like in a waveguide. We'll explore that channel in a later episode. For now, one idea is enough. There are depths where sound becomes astonishingly efficient. In those layers, the ocean behaves like a giant acoustic resonator. For submarines, that is both a gift and a threat. You can hear more, but you can also be heard from farther away. Now we arrive at a word you've probably heard many times, often without a clear picture of how it really works. Sonar, sound navigation and ranging. Sonar is the underwater equivalent of sensing the world, but with pressure waves instead of light. In very broad terms, there are two main ways to use it. Passive sonar, listen to the sounds the world already makes. Active sonar, send out a pulse and read the echo that comes back. We'll dedicate a full episode later to tactics, clever tricks, and the difference between passive and active. Here, we just need the basic idea. One-sentence example. A submarine may never see another sub directly, but it can see it as a pattern of engine hum, propeller noise, and returning echoes. But sonar never operates in a vacuum. The ocean is never truly quiet. Even far from ships and cities, the sea has a constant background sound. Waves breaking, wind pushing the surface, distant storms, rain, tiny animals snapping and clicking. All of this adds up to a permanent underwater hiss. Engineers call this ambient noise, the acoustic wallpaper of the ocean. For a submarine, this is both a curse and a shield. If your own noise is much louder than the ambient noise, you stand out clearly. You rise above the wallpaper as a distinct pattern. If you manage to stay below that moving baseline, you start to blend in. You become just another texture in the hiss. One-sentence example. A submarine that is quieter than the sea around it can disappear into the hiss, while a noisy one shines like a flashlight in a dark room, even if nobody can see it. This is also where the idea of an acoustic horizon becomes practical. You can only detect a sound source as long as it rises above the ocean's ambient noise. Beyond that distance, it still exists, but it drowns in the hiss. Different oceans, different weather, different depths, all of them change how far that acoustic horizon stretches. Underwater, you are not just hiding from other submarines. You are hiding inside the sound of the planet itself. To feel this more intuitively, think about how we hear on land. On a quiet night, you can hear a car long before you see it. The low rumble of the engine, the rolling of tires, wind noise. In a city at rush hour, that same car might be almost inaudible, buried under traffic, people, ventilation systems, and distant sirens. The car does not change, the background does. Underwater, submarines live in exactly that kind of trade-off. Their own noise stays roughly the same, but storms, waves, rainfall, ice, and distant shipping constantly redraw the acoustic background. Above the surface, sight dominates because air is clear and light is cheap. Underwater, everything reverses. Light fades in tens of meters. Sound travels tens to hundreds of kilometers. And careful analysis of sound reveals structure in what looks like total darkness. That is why, in practice, submarines are designed around their ability to hear. A modern submarine does not have human-like ears. It has arrays, long lines and large surfaces of sensors along the hull or in towed cables stretching behind the boat. These sensors detect tiny pressure changes caused by sound waves. Because the sensors are spread out in space, the system can determine direction, separate overlapping sound sources, estimate speed, and sometimes even classify what type of ship or submarine it is listening to. The result is an acoustic map of the surroundings, a three-dimensional image built entirely from sound. One-sentence example. Where humans rely on a visual horizon above the surface, a submarine works with an acoustic horizon, the distance out to which sounds stand out from ambient noise. This may feel like magic, but it is simply physics and engineering applied with patience. Water carries sound well, kills light quickly, and allows tiny pressure changes to encode massive amounts of information. But there is one unavoidable consequence. If sound travels far and can be decoded precisely, you are also easier to detect. Every sound a submarine makes, from pumps and coolant systems to the turning of its propeller, risks leaving a trace across long distances. That's why undersea warfare is far less about dramatic chases and instant reactions, and far more about a slow, quiet contest of silence. Future episodes will follow that contest in detail. How propellers are shaped to delay cavitation. How hulls are decoupled and damped. How sonar extracts faint patterns from a sea of noise. Today was the first step, understanding why the eye of the deep is not an eye at all. It is a sensor built for pressure waves. At the end of this episode, you can picture the ocean differently, not as a dark emptiness with a few beams of light, but as a dense world of overlapping invisible ripples. Every whale, every ship, every submarine writes a pattern into that field. And anyone who learns to read those patterns can see, in a world that to human eyes looks completely black. Sound rules the deep. Everything else is decoration.